In this video, we will learn how to describe primary cells and explain how they produce electrical energy. In the first section of this video, we'll see how electrical energy comes from cells used in portable electrical devices that we see in everyday life. Portable electric devices, like torches or flashlights, get their energy from chemical reactions that take place inside electrical cells. Electrical cells are often referred to as batteries, although a battery is strictly several cells connected together. A primary galvanic cell is a single-use electrochemical cell where electrons are generated through a spontaneous redox reaction. When the circuit inside the flashlights is completed by closing the switch, electrons flow around the circuit as a result of spontaneous chemical reactions in the cells. The flow of electrons results in an electric current. Since electrons carry an electric charge, an electric current is a measure of the rate of flow of electric charge. The type of chemical reactions that occur in each cell are called redox reactions. In a redox reaction, electrons are transferred from one chemical species to another. Redox reactions therefore involve species being either oxidized or reduced. If a species is oxidized, it loses electrons. If a species is reduced, it gains electrons. Oxidation and reduction are easily remembered using the mnemonic oil rig. Quite often, flashlights are powered by relatively cheap zinc-carbon cells. These cells have a zinc casing, and in the reactions that drive these cells, the zinc loses electrons. The zinc casing is therefore the site of oxidation. In a galvanic cell, the site of oxidation is the negative electrode. Sometimes this is also referred to as the anode. Electrons are transferred from the negative electrode to a carbon electrode, which is the positive electrode in this cell. In a galvanic cell, the positive electrode is the site of reduction. It's also known as the cathode sometimes. The carbon cathode collects electrons and it is surrounded by a paste containing manganese dioxide. Manganese dioxide accepts the electrons in a reduction reaction. So overall in these cells, electrons flow from the zinc anode to the carbon cathode. Of course, electrons also flow through the light bulb, which causes it to light up. The chemical reactions in the cell continue until all of the reactants are consumed. The zinc casing will become thinner as the zinc turns into zinc ions in the electrolyte in the cell. The chemical composition of the manganese dioxide paste will also change in the reduction reaction. Over time, the bulb will become dimmer and the cell is eventually spent or discharged. It can only be used once. It's then discarded or recycled to recover any contents of value. Primary galvanic cells operate in this way. The chemical reactions that take place spontaneously inside them are not reversible. So when the flashlight stops working, the cells inside it cannot be recharged. In the next section of this video, we'll take a detailed look at a specific type of primary galvanic cell called the Mercury cell to understand how the electrons flow within it. The Mercury cell consists of a steel can that acts as a container, but it's also in contact with mercury 2 oxide that has the formula HgO. This part of the cell forms the positive electrode or cathode, which is where a reduction reaction will take place. The cap of this cell is in contact with zinc metal, and this forms the negative electrode of the cell. The negative electrode, or anode, in this cell is where an oxidation reaction will take place. Use the mnemonic CROA to help remember where reduction and oxidation take place. The cathode is the site of reduction, and oxidation takes place at the anode. A porous separator keeps the chemicals in the anode and cathode apart. The porous separator contains electrolytes that allow for the movement of ions and hence charge to complete the circuit when the battery or cell is operating. To prevent a short circuit in the cell, an insulating seal separates the anode and the cathode. It also contains the chemicals to stop them leaking out. Now let's take a look at the chemical reactions occurring in this cell and the voltage that it generates. At the anode or negative electrode in this cell, electrons are lost. An oxidation reaction occurs. Zinc metal is oxidized to zinc oxide. At the positive electrode or cathode in this cell, mercury 2 oxide is involved in a reduction reaction. Mercury 2 oxide is reduced to mercury, which is a liquid metal in this cell. By adding the two half equations together, we get the overall reaction that occurs in this cell. Zinc metal reacts with mercury 2 oxide to produce zinc oxide and mercury. When we added the two half equations together, the 2 moles of hydroxide ions on each side of each half equation cancelled each other out. This also happened for the 1 mole of liquid water molecules on each side. The electrons also cancelled out, as there were 2 moles of electrons involved in the oxidation process and 2 moles of electrons involved in the reduction process. To calculate the E standard for the cell, that is the cell EMF, or the voltage produced by this cell, we need to know the standard reduction potential for the cathode and the standard reduction potential for the anode. We simply subtract the standard reduction potential for the anode from the standard reduction potential from the cathode. Standard reduction potentials are measured against the standard hydrogen electrode under standard conditions. The standard hydrogen electrode is by reference given a voltage of 0 volts. The standard reduction potential for the anode in this cell is negative 1.25 volts. In this cell, the standard reduction potential for the cathode, where mercury 2 oxide turns into mercury, is positive 0.0977 volts. The voltage produced by this cell under standard conditions is therefore positive 0.0977 volts, subtract negative 1.25 volts. This voltage has been rounded to 2 decimal places. Since mercury cells contain toxic mercury compounds, they're not produced in large quantities anymore. Because the cell could be manufactured to be very thin, these batteries, or cells, were known as button cells, and they were used widely in watches, hearing aids, and calculators. Since the chemical reactions in this cell are not reversible, the cell cannot be recharged. This type of cell would need to be either disposed of carefully or recycled due to the toxic mercury content. In the next part of this video, we'll take a look at hydrogen fuel cells. Fuel cells are a type of galvanic cell where the chemical reactants are stored separately outside the cell. The reactants are fed into the fuel cell where the chemical reaction takes place. The redox reactions inside the fuel cell can provide an electric current on demand. This might happen when a device like an electric motor is connected to the fuel cell and is doing work. The fuel cell will produce a constant voltage provided the reactants are fed into the fuel cell at a constant rate. The most common type of fuel cell is the hydrogen fuel cell. Hydrogen gas is fed into the cell from an outside store, where it reacts with oxygen gas, which is drawn in from the outside air. Inside the fuel cell, the anode and the cathode are separated by an electrolyte-filled membrane. In the acidic hydrogen fuel cell, the membrane is filled with an acidic electrolyte. At the anode, hydrogen gas is oxidized and electrons are released. These can be made to flow around an external circuit through an electric motor, for example. The remaining hydrogen ions, or protons, migrate through the electrolyte membrane to the cathode. In the acidic hydrogen fuel cell, the membrane is frequently referred to as a proton exchange membrane. At the cathode in the fuel cell, oxygen gas is reduced. Oxygen molecules gain electrons returning from the external circuit. They react with hydrogen ions and they form water. Whilst producing electricity, the hydrogen fuel cell makes water as the only waste product. This type of fuel cell has been used to produce electricity in space travel, and it also produces electricity for some electric cars. Let us take a look at the reactions occurring at each electrode in more detail. At the anode, hydrogen gas is oxidized. Hydrogen ions and electrons are released. The standard reduction potential for this process is 0 volts. At the cathode, we saw that oxygen gas gains electrons and reacts with hydrogen ions to produce water. The standard reduction potential for this reaction is positive 1.23 volts. We can balance the electron transfer in each half equation by multiplying the top equation by 2. The overall equation for the reaction occurring inside the fuel cell is then obtained by adding the two half equations together. The equation simplifies to 2 moles of hydrogen gas reacts with 1 mole of oxygen gas to make 2 moles of water. The standard cell potential for this fuel cell can be calculated using the equation standard cell potential equals the reduction potential of the cathode minus the reduction potential of the anode. For this type of fuel cell, the standard cell potential is positive 1.23 volts. The cell voltage remains constant as long as the reactants are supplied to the cell at a constant rate. Since water is the only waste product, the hydrogen fuel cell provides a source of electricity that does not directly produce carbon dioxide. Carbon dioxide is emitted by combustion engines in cars. One idea is to replace combustion engines in cars with fuel cells to power electric motors. We must consider, however, that the hydrogen gas for the fuel cell must be manufactured since it's not available in our atmosphere. A hydrogen fuel cell may also operate in alkaline conditions. In the alkaline fuel cell, oxygen gas is fed to the cathode where a reduction reaction takes place. Oxygen molecules gain electrons and react with water molecules to produce hydroxide ions. The hydroxide ions move through an alkaline electrolyte membrane. Hydrogen gas is fed to the negative electrode or the anode. At the anode, hydrogen reacts with the hydroxide ions that have moved through the alkaline electrolyte membrane. Since electrons are produced at the anode, and the anode is at a more negative electrode potential than the cathode, the electrons can be made to flow around an external circuit where they can do work. The electrodes are often made from ceramic materials coated in a thin layer of platinum, which helps to catalyze the reactions. It may come as a surprise to see that the cell potential for the alkaline fuel cell is the same as the cell potential for the acidic fuel cell when under standard conditions. However, when we add the two half equations together, the overall reaction in the alkaline fuel cell is the same as the overall reaction in the acidic fuel cell, so the voltage produced is the same. Now it's time to look at a question to test our understanding of galvanic cells. Which of the following reactions is the half equation for the reaction that occurs at the cathode in a mercury cell? To answer this question, we need to remember that the cathode is the site of reduction in a galvanic cell. In a galvanic cell, oxidation happens at the anode. In a reduction reaction, electrons are gained. So we're looking for a half equation where the species on the left, that is the reactants, gain electrons. The electrons have to appear on the left side of our half equations. We can rule out answer C as the electrons are being lost in this half equation. This half equation represents an oxidation process. We can also rule out answer D as this is not a half equation, it's a full redox equation. In D, zinc loses electrons, its oxidation state increases and it's being oxidized. Hg, or mercury, is being reduced, it gains electrons as its oxidation state decreases. For the same reason that we ruled out answer C, we can also rule out answer E. Although it appears to be a half equation, we can see that the electrons appear on the right-hand side. They're being lost, and it's an oxidation reaction. Remember, we're looking for a reduction process. On closer inspection of answer B, we can see that there appears to be no redox processes taking place at all. The oxidation state of mercury remains at +2 throughout the equation. Since we're looking for a reduction reaction, it can't be the right answer. Mercury cells contain mercury 2 oxide, or HgO, at the cathode. In answer A, we see mercury 2 oxide gaining electrons. Mercury 2 oxide is the correct species for the cathode in our cell, and it's involved in a reduction reaction here. This is the correct answer. Now it's time to review the key points from this video. A primary galvanic cell is a single-use electrochemical cell where electrons are generated through a spontaneous redox reaction. Reduction happens at the cathode, oxidation occurs at the anode. The standard cell potential can be calculated by taking the standard reduction potential of the cathode and subtracting the standard reduction potential of the anode. Fuel cells are a type of galvanic cell where the reacting components are constantly supplied.